So just to reiterate, changing the number of protons changes the identity of an element. Changing the number of electrons by comparison only changes its charge. It forms ions. Now this is a new vocab word, or maybe new to some of you, is an ion as a charged atom, a charged particle. However, there's two other additional terms that we could use because these refer then to specific types of charges, positive or negative. For a positively charged ion, those are called cations. Now you could remember that cats have paws and cats are positively attractive. Or you can remember that the word cation has a positive sign here in the middle of it with the letter T, but cations are positively charged ions. For negative ions, we call those anions. And changing in the ions, changing the charge affects the relative stability of an atom, it affects its chemical properties, and how different elements and atoms react with one another. Again, just to review, changing the number of neutrons changes the mass of an atom, leading to what's called the formation of an isotope. And as we discussed last week, isotopes vary based on their stability because the number of neutrons helps keep the nucleus together and it helps prevent the protons from repelling each other and the nucleus breaking down. For isotopes specifically, if we look at something like magnesium, magnesium has three different naturally occurring isotopes. We can have magnesium with a mass of 24, 25, or 26. Now each of those has an exact mass that's a little bit slightly different than that because we just said that earlier that protons and neutrons have the same mass as each other and it's both about 1. However, it's not exactly 1, so that's where this exact mass comes into play here. Now the discrepancy we run into is we had said that the mass on the periodic table was called the average atomic mass. Now the problem is if we were just to take these three mass numbers, add them up and divide by 3 to get an average, we would get 24.9845, which does not match what's on the periodic table. So this is a problem. Here we have an average on the periodic table, but it doesn't seem to be the average of just those numbers. The reason this happens is because not all three of these isotopes are as common as each other, right? They're not as common in nature because the ones that are less stable break down faster. So for example, if we had a bar of magnesium, such as this blue square over here, we see that within that bar, within all of that magnesium, because it is the same element, some of those atoms have different masses than each other. And how common and how frequent these are is something that could be measured through using a tool or a process called mass spectroscopy. But that's something to get into for another time. The important thing to know right now is that when we look at the different isotopes for elements, we see that they're not all equally abundant. And in fact, for magnesium, more often than not, most of the time, the isotope of magnesium that we find is magnesium 24. And because it is so much more common than the other two, we can infer from this that this one is the most stable as well. It's the least likely to break down and turn into something else because it is more common. Whereas these two, because they're so rare by comparison, these two must not exist for very long. And their half-life, as we call it, is very short. So what this affects our mass and our average is because if we were to pick an atom at random out of this block, odds are we are not going to choose a magnesium 25 or magnesium 26. Odds are we're going to take magnesium 24. And so if we're going to have an average for a mass, it should reflect what the particle is on average, but on average, it is not magnesium 25. It's most likely going to be magnesium 24. So we need to have a way to calculate an average that accounts for this idea that not everything is equally weighted or as equally as common or counts for as much as each other. And the way we do this is by doing something called a weighted average, which is something that we've done probably before, because this is actually how we calculate grades for a class. Because we know that for different classes, you have different categories, and the categories are weighted differently than each other. In this case, these are the category weights for chemistry, and we see that our assessments are worth most of our grade. So any change in this and the assessment grade is going to have a bigger impact than a grade in the daily work. The way we turn this into an average and actually find the marking period grade for the Greg in this case is doing what's called a weighted average. Now the general format for a weighted average is to take the value that you're looking for, or the value that you're trying to average with each other, and you're going to multiply it by its weight, right, the category weight. But we don't want the percentage, we want to make it back into a decimal. So since these are percentages out of 100, it's going to be the weight out of 100. And then all we're going to do is we're going to do that for each of the values, and we're going to add them all together. So we're going to do the first value, the second value, and we're going to continue doing that on and on and on until we run out of values. So specifically for Greg's marking period average, he had a 65% in his assessments category, and the assessments were worth 50% of his total grade. In his labs, he had an 88%, and they were worth 30% out of 100. And then lastly, on his daily work, he had a 90%, and that category was worth 20% out of 100. To get this in the calculator, I recommend getting an answer for each of these three parts here, and then adding those three sections together to get your final answer. The reason I recommend this is because once we start applying our significant figure rules to the measurements, when we start doing this for our weighted averages with isotopes, it's going to make the most sense in terms of the rounding. So for this first section, we would get a value of 32.5. For the second section, we would get a value of 26.4. And for the third section, we get a value of 18. So in total, we add those three things together, and his grade for the marking period would be 76.9. Now we see that compared to his values up in his initial grades, it is closer to the lower grade, which is worth more, compared to if we were just to take an average of his three grades, 65, 88, and 90, right? An average that would assume that all those things are weighted equally to each other. His regular average would come out to an 81. So we see that by doing a weighted average, it shifts the average closer to the value that is worth the most, in this case, the 65. We can apply the same thing to our weighted averages, except now instead of the category weights for a class, we're talking about percent abundances and commonality in isotopes. So if our goal for our weighted average is to find the average mass, then we need to take the mass values as our values in the formula. So for the first one, we would have 23.9850 times its first weight or category abundance, 78.99 out of 100. Now here I'm putting 2 decimal points onto my 100 because if I add up my abundances here, remember the rule for adding and subtraction is that we're going to keep the lowest number of decimal places, and that was 2 in all of these cases. I'm going to add that to my next value, which was 24.9858. We're going to multiply that by its value, its weight. And then I'm going to do the same thing for the last one. So here again, we're going to solve this by getting 3 different pieces. And the reason we're doing that is because here in this, we're taking multiplication and division and addition and subtraction rules for sig figs, and we need to apply all of them to this problem. So the first thing I'm going to do is multiply the first value times its weight divided by 100.00. And without any rounding at all, as a raw number, I would get 18.9457515. For the second set, taking 24.9858 times 10 out of 100 without any rounding gives me 2.49858. And then for the last component, we would get 2.861. Now for significant figures, we're going to round each of these to the lowest number of significant figures because that is the rule for multiplication and division. So for this first section, we're rounding to 4 sig figs because of the 78.99. In the second section, we're also rounding to 4 significant figures because of the 10.00. And then same thing here in this last section due to the 11.01. So this becomes 18.95 plus 2.499 plus 2.861. Now when I ultimately add these together to get my weighted average, again without any rounding, I'll write my raw answer. 18.95 plus 2.499 plus 2.861 gives me a value of 24.31. Now I need to ensure that I have the right number of decimal places because that's the rule for addition and subtraction. Here we have 2 decimal places, 3 and 2. So I need to round this to 2 decimal places, which it currently has, making 2431 our final answer. If we compare that back to the weighted average for magnesium on the periodic table, remembering that we're always going to round these numbers to 2 decimal places, we see that we have a perfect match.